Hey everyone. Today we're going to look at electric fields and forces. So today we're going to, by the end of the lesson, as long as you can tell me which direction a charge gets pushed, like if they're attracted or repelled, and you can draw an electric field, then you'll be all set. So let's start with this, attraction versus repulsion. So charges interact with one another. Like if you have a positive and a negative object, they'll either push or pull on one another. But how do you know which? Well, our rule here is that opposites attract, and by opposites I mean a positive and a negative. So opposites will attract one another, which means that they'll be pulled towards each other. And then like charges, when I say like, I mean they have the same charge. So like charges repel. So opposites attract one another, they're drawn towards one another, and like charges will repel one another or push away from each other. So, nice question would be, state whether each of the following pairs of particles would be attracted to one another or repelled from one another. A proton and another proton for number A, or part A. Okay, well, protons are positive, right? So we've got a positive and a positive. I would say those are like charges because they're the same. They're both positive. So they will repel each other. Which basically means that if you put them near each other, they push away from each other. An electron and another electron. Well, electrons are negative. These are both negative. And like charges, meaning they're both the same, they're both negative, will repel each other. So again, two electrons, if you place them near each other, are going to push off, away from it. They're going to separate. A proton and an electron. Well, one's positive, the other's negative. Those are opposites, and so those will attract. So if you put a proton and an electron near each other, they will move towards each other. You're going to like sort of feel this force of attraction smushing them together. Okay, so what does this actually look like? Well, on each of the following diagrams, draw an arrow to indicate the direction of the electric force acting on the charge. So we've got a positive here and a positive here, and again, two positives, kind of like we said for part A up here, will repel each other, which just, again, is just a word that means pushing off, away from each other. So this object will move away, and then this object will move away. That's what I mean by repel. They're both trying to get away from each other. So this one's going to move to the right, this one moves to the left. Here, I apologize for the sideways negative. I'm not sure what happened there, what I was doing. But we've got a negative and a positive. Are they attracted to one another or repelled from each other? Well, these are opposite charges. So they're going to move towards each other. The negative is going to move this way, towards the positive, and the positive will move this way, towards the negative. They're attracted to one another. Last up, we got two negatives. Alright, those are the same charge. They're like charges, and so they will repel each other. So this negative is going to get pushed that way, and this negative is going to get pushed that way. Cool. Attracted versus repulsion. So opposites attract, likes repel. If you remember that, good for this part. Next up, electric fields. Okay. Alright, electric field. So what you have to be able to do here is draw the electric field in the space around an object. So let's start with what even is an electric field. A field is this sort of like unique or unusual thing that we do in physics. A field is kind of like, it's like a map. I'm going to put map in quotes because it's kind of a jump here. It's like a map of the forces in the space around an object. Let's go with a charged object, because this will really only be present around electrical charges. So if you have a charged object, it's surrounded by an electric field. And what a field is something we use in physics for like forces that can reach out across space and grab objects. A nice example of something we've already studied that has a field is gravity. And we didn't talk too much about gravitational fields, but gravity can reach across space and grab objects. And so we can represent that force using something called a field, which again is like a drawing in the space around an object, like the space around the Earth, for instance, that shows the direction that the force is pushed. And gravity is pretty simple because it's like always attractive. It always pulls towards the Earth. But for electricity, since we have these positives and negatives that sometimes attract and sometimes repel, it's a little bit more complicated. And so it's a slightly more complicated set of rules. And you need to be able to draw the field around an object. If you can remember these 3 rules, then you'll be in great shape. Our first rule, rule number 1, it's probably the most important one, or it's at least the one I'm going to ask you about the most, is electric fields always point. So electric fields, we draw them with arrows, and those arrows always have to point away from positive charges, and they always have to point towards negative charges. So that's the rule that, again, whoever got to this first decided that that's how we're going to do it, so that's how we're going to do it. Electric fields always point away from positive charges and towards negative charges. So if you have like a positive charge, the field will point away from it. If you have a negative charge, the field will point towards it. Again, that's just the rule that we use. Cool. The next thing is, if you're drawing an electric field, when you draw them, the field lines never cross. The Ghostbusters rule, never cross fields. Field lines never cross. So if you draw, let's say we've got a positive and a negative, and you draw them going away from positive towards negative, and you're like, I'm great because I remember they go away from positive towards negative. See how they cross right here? That's bad. That's not what happens. So what it actually would look like is that it would go away from positive and towards negative, something like this. And if you're drawing these and you cross the fields like that, that's bad. Something went wrong there. So these field lines do not cross one another. Lastly, it's worth mentioning, but probably the least important, the closer the lines are, the weaker the field is. The closer the lines are, the weaker this field is. So let's say we've got some sort of unusually shaped electric field. Let's say it goes like that, it goes like that, and then it goes, I don't know, let's give it something like this. Okay, this would be a weird electric field, but, you know, could exist. So, the closer the lines are, oh, I said this all wrong, I'm so sorry. Oh, erase that. I don't have the video editing software to go back and fix that. So closer lines equals a stronger field. Hopefully you weren't jumping around the video then. Oof, I apologize. I have to pay money for the editing software, so I'm not going to do that. So, so we're just going to go with this. The closer lines are, the stronger the field is. So if we have this electric field right here, the field would be the strongest right here. Let's change color for this. Here we go. So the field would be like strong in this region right here. And it would be weak like up here and down here. And the reason it would be weak there is see how spread out the lines are? They're not close together, so the field is sort of understood to be weaker there. What could I ask out of you? I could ask you to draw the electric field around a charge. So that's what we're going to do. These are sort of like all the different ones I could possibly ask you. So let's go. We've got a negative charge. Do they point towards negative or away from negative? Towards negative. Why is that? Because I told you so. Because that's how physicists decided, that's how we'll do this. Always away from positive and towards negative. So what we're going to do is we're just going to surround this with arrows that point inwards. And that's the electric field. That's what it looks like. Again, it's like a map of the forces around the object. We also said they point away from positive, so probably something like this. There we go. It should be ideally be symmetrical. I've got all these dead spots on my computer screen, so a lot of these lines got kind of cut out. These lines should be straight, and they should have arrows pointing away from this positive charge. So 2 positives. Let's start with what we can do. Now, it seems like they should just come outwards, right? Like outwards, outwards, but the problem is then they cross, and that's not good. It's not exactly what happens. what actually happens is they'll come out of positive, and since they can't cross, they kind of like bend away from each other in something that looks kind of like this. Again, if I could draw this well, it would be symmetrical. I don't think it's really symmetrical the way I did it, but it's okay. So we're away from positive. If you drew it out here, it would probably be like kind of something like that, maybe. But what I'm really interested in is the space in the middle right here, where the lines sort of go and then they bend away from each other. Two negatives looks kind of the same, except that instead of pointing outwards, the lines will point inwards, because these field lines always point away from positive and towards negative. Last up is here, away from positive towards negative. So the field looks kind of like this. Oh god, I feel like this didn't turn out very nicely. It's okay. There we go, and these should all have arrowheads pointing away from positive and towards negative. So again, it's like a map of the forces in the space around an object. And these are like real things. I know this like seems weird that objects are like surrounded by these arrows and whatever, but it's a real interaction that occurs in the space around an object. So here's a pretty good video on YouTube that kind of actually does a good job of showing these electric fields in action. So we've got, here we go. We put these little crystals on like a sheet of paper, and these crystals release a dye. And then if I pause here, this spot right here and this spot right here are opposite charges. So that field, it comes out, it bends away and goes back towards the other one. So the field we're kind of looking at is something like this. And if we go here, again, we put these little sprinkles down, and what they actually do here is they release this like ink or dye in the space around it, and you can kind of see that like upwards and curving back type of like action. So this electric field, it is a real thing that you can observe. Here we've got a single charge, and notice that, again, that field kind of radiating outwards, going towards this other metal object, which I'm assuming is also charged. And then here we just have a single charged object, and again, we sort of radiate outwards from there, and you can see that sort of what you're looking at is something that's kind of like one of these. I don't know if it's positive or negative, but see these lines pointing directly in and directly out? That's what we have. So it's like, this is a real actual electrical interaction in the space around an object. And then last up, we have two oppositely charged plates. So like this one on the left might be positive, this one on the right might be negative, and so these lines cross, go directly from one towards the other. And you can make these as complicated as you want, and again, this just like feeds you like a map, or shows you these electrical interactions in the space around the object. Okay, so those are the ones we did together. Just like all these videos, I'm going to have you try 16 through 19 on your own. If you're stuck, just don't worry about it. Go on to the next one. See what you can do. I'll give you a second to try these on your own. So pause the video, give them a shot. Alright, I hope you paused it and tried them. Here's the answers. The proton is placed between two charged plates as shown in the diagram. Which plate would the proton be attracted to? Well, protons are positive, right? Oops. But a positive object. A positive object. Which of these two plates do you think would attract a positive object? I think this bottom one would. So which plate would it be attracted towards? I'm going to say the bottom one. And the reason for that is opposites attract. So this positive would be attracted towards that bottom plate, because opposites attract. Alright, how does the electric force explain why electrons remain in orbit around the nucleus of an atom? So this one's kind of a thinker. But let's do this. When we have an atom, remember, it's a bunch of particles in the middle of an atom, and then the electrons surround it in these sort of like orbits. That's a pretty good drawing of an atom. So we've got these particles in the middle. Remember, those are the protons and electrons, which means that, those are the protons and the neutrons, which means this nucleus has a net positive charge, and this has a negative charge. So where does the electron want to be? Well, it wants to be near this nucleus, as much as sort of the structure will allow it to. So again, it wants to be near that nucleus. And so that's why it won't, like, fly away, because it's attracted to that nucleus, right? If it wasn't attracted, it would just go wherever it wanted. So, and again, the idea is that it is, if we had to say this in as few words as possible, it is attracted attracted to the nucleus. There we go. That works. Okay, draw the electric field around the following charges. So this first one is not one that we did earlier, but I think we can kind of figure this one out. We said that electric fields always point away from positive and towards negative, and so our field looks kind of like this. Away from positive, towards negative. Here, the two positives looks kind of like one we did earlier. Those fields that go away from positive, but since they can't cross, they're going to bend away from each other. Kind of like this. It's got a bunch of dead spots in it, but that's the idea. Lastly up, a single negative charge. Well, we said electric fields point towards negatives. So it'll be kind of like this. There we go. 19. A newly discovered particle is found to repel electrons. What is the charge of this particle? Well, electrons are negative, remember, and if it repels them, well, like charges repel each other. So this object must also be negative if they repel each other. Okay, that's it. So what I wanted you to get out of this is, to make this kind of as short and simple as I can, opposites attract, like charges repel. And I want you to understand that fields are this map of the forces around an object, and that you can draw them basically by following this set of rules. Everything I would possibly ask you is kind of in this setup right here. These fields point lines, they point away from positive and towards negative.